Hello everybody, so welcome back to another tutorial on our RTS journey in making inside of Godot. So I'm going to go right ahead and show it to you, but I'm going to turn off the transparency for this sprite so I can show you the change between states for these units because the transparency is mixing with the label here. So as you can see, whenever the unit is moving, we change to the state number 3. So the state number 3 is states moving, and as you can see here, all the units now use this behavior. So the units does not move if it's already moving, and that is part of the state machine process that I have implemented. So what's the trick here? So feature side, yeah, nothing has changed yet again, but behind the scenes a lot is happening. Now we have state machines for our units. So before I jump ahead in the code and update the project in this part, I'm going to go back here towards the drawing boards to show you a resume of how I implemented everything that I have tried to discuss in the previous part about the state implementation stuff. So everything I planned for the state thing and how I actually decided to implement it inside of Godot. So the first thing is the state specialization behavior versus the modularity. So one of the issues was how you can keep states modular while still having a way to specify everything they have. So the way that I have decided to do is to keep states generic. So we only have state like idle, move, and attack, and they not specify if they are for boats or airships. They don't specify anything. The specification comes inside of the code using qualifying guards. So what this means? Well, this basically means that if for an idle state for a worker we want to gather resource, we can simply check if that unit has the worker flag or another property in order for us to scan for resources. And this somehow makes units more predictable as well. And it still allows us to keep a unit to be a worker and an attacker at the same time. Now, because this script has priority, the first one will be executed, but if we wanted, we can also do this as a inventory of dictionaries, so we can store each one of those inside of it and execute them based on that. Or we can even pass priority list to execute which ones we want. If we wanted to prioritize one over another, otherwise it's going to execute in this order. If we make a unit that is both a worker and an attacker, is going to first execute the attack code, then the worker for the idle state of these units. But as you can see, doing it this way, we basically qualify the states whenever we want to do something specific. Likewise, for instance, here we want to make units fly or swim, we can basically check if they have water movement or air movements. In the case of our artillery example, we had lots of issues with regarding how to make a unit attack if it's just a simple unit and mount if it was an artillery unit. Well, in this case, we can also qualify if it has an artillery mount flag, or we can simply attack if it is a common military unit. So as you can see, doing this way, we keep states as individual. So they are still encapsulated and modular because we can apply the states to every single object. And based on flags, we can basically specialize their behavior to be like a building idling is going to be executed different. So for instance, a turret on idle mode, if we have here a flag for that, it's going to check for enemies and call for a state change to attack, but it's not going to move because movement is not the turret. So yeah, this allows us to keep things simple using a basic structure like idle, move, attack, and doing specialization inside of the code using guards, we can do specific things inside of the object. So this is pretty much as we want. And if you want to encapsulate more functions or keep things more modular, we can split functions inside another script, etc. So this is the system that works pretty much as I wanted. The state execution itself, it's also simple. We only have 3 things we need to keep in mind for every single state. Every single state needs to first enter its state, then exit the previous state and execute the current state. So the enter state is going to happen whenever you enter a new state. But before you enter a new state, you need to exit the previous state first. So that is the execution order. And the execution of the state currently I am doing through the physics process of the units. So The state transitions work as the following: a unit or the interface for the player or the AI for a enemy player is going to request an unit to move to another state, so it's going to change the state. We're going to do the state transition using a state main manager, just like action manager and the object data manager, and it's going to have a function that's going to do just these 3 steps here. The first step is to detect the current state for the unit so we can exit out of it to execute any code that's going to clean up the state machine so the next state can work with it very much seamlessly. Then next we're going to enter the new state, which allows us to set up vars if we need animations and stuff. And finally, we can execute through the physics process or an update function the current state which have the methods we want. So this is how state transitions are going to work inside of the current RTS project I have built. And if we want to specify more complex things, I think we can do this inside of a project later as well. The last thing is we need to pass state signals, because you're going to be in the idle state and you're going to find, let's say, an enemy. So this allows us to respond to signals based on the current state we have, and we can also do logic with specialized behavior, just as we did here, for the states to move or attack based on a collection of attributes or flags. This allows us to pass the same state signal, and through the different states we can process different logic. For instance, we can request movements to both of these states, but each one is going to handle it different. So if you are already moving, you're going to simply update the position. If you are idling, however, then you're going to generate the first path in order for you to move. The same thing for an enemy found. So if you are idling, you can basically just follow the enemy you found because you don't have a target yet. Whereas if you were already moving, maybe pursuing another enemy, and you found another enemy, then we can say you get the closest enemy you find or the weakest one. So doing this way, we can pass signals, so the same signal can be passed to different states and they can process it in different ways as they want, based also on their character attributes. So I think this is how I'm going to simulate and pass signals through the states. And the signal I want to specify here is just an integer. So I'm not even using Godot resource signals with strings to pass a signal to another object. So every single state can basically execute a signal, and this signal can do anything we want based on the logic of the current script. So we can pass a request movement. If we are already moving, we do XYZ. If we request the movements and we are idling, we will do something else different. This allows us to communicate between different states and different objects using this methodology here. And of course, if we don't want to process the signal based on the state we are, we can also ignore it. So we can process the signal if you are on the idle, but not process on the attack. We basically just ignore it on the filter. So this is basically how I implementing the state machine for every single object in the game. And there's not even actually a finite state machine. The states are completely isolated in different scripts. So we have a state for the idle, for the movement and attack, and they are isolated from the object. So this is pretty much a modular system, very simple and very efficient. And we're going to see how I'm using it in my project here. So if I open the current project, here is how everything is working. And as you can see down here, we have an object state under the RTS scripts, which has a bunch of stuff. The constants for every single state we want, a signal list, and just as we have with object data, and for the constants of the action list. So yeah, this is very simple. And here we have the main state manager, which basically does everything we have discussed under the presentation. So it has the constants and aliases to short the code. We have the state scripts, which at the moment only has idle and movement. We have the function that's going to switch states. So first we need to grab the current state, doing it this way. So we access the current object, and through the data manager request the data value from the object current state. Then we exit out of that state and we enter the new state. Once we enter the new state, we're going to simply access all the state scripts and through the state we have passed under this function, we're going to ask it to enter. And this is going to be the responsibility of this state. So this enter state function belongs to the state script. So every single script is going to have an enter, exit, and execute state. And whenever we enter a new state through the change state function, we're going to ask that state to enter itself. So this is going to allow us to set things like change the state of the objects to be idle if it was an idle state, or if it was a movement state, we can simply change it to be move. Under the exit state, we can also execute special code. So say something for like if you want an animation to be performed or something like that, we can do that in the exit stage as well, or set variables. The execute state can be the execution of the state logic itself. So this, I think, it's where the most complex things are going to happen. And here, for instance, for the state movement, we can say that if we have a path, once we are executing the state, we're going to follow that path. And this code here was how the unit was moving previously, whereas now we are doing it through the execution of the state movements. So this is very powerful and very useful. And as you can see, we also have the execute signal here. So for the stuff we have talked about, whenever we want to pass signals towards other states, this is how we are performing it. We're going to first grab the current object state in order for it to receive that signal. So we are going to access the current state, and through the state scripts we have stored in the main manager, and through the object current state we're going to ask it to pass this signal, and we're going to pass the object reference and the signal integer. This allows us to process that signal as you see here. So for the state idle, you can see that execute signal needs the object reference that it is executing the signal and the signal itself. And we also need the current object state, because here is where we filter things out. So as you can see here, we have a state, a match here for both arguments. So we need to match both of these variables with the match statement. First, we need to match the object state, then the signal itself. So say that you want, if we are in the state idle and we have received a signal to move the object. So here this says that the object state needs to be idle and the signal passed needs to be the signal request to move. And we can basically duplicate this for other signals as well. So say that you want to make a attack signal, we can basically do it just like this. However, I don't have here the current one, so this I think is going to throw an error because attack does not belong on the signal list. So as you can see, this is how you can perform signals. In our case, if we are idle and we want to move, we're going to grab the new path goal. We're going to generate from the action scripts for the action move, which has a path new, which needs a goal and the object itself. So from the call of this signal under, if we are on the state idle, we're going to change the states to the new one, and this is using the script state manager. So this is not directly accessing any other state. It's going to say to the state manager that it has to change the state. So the state transitions are done using the state main manager, not the object and not the other states. This keeps things clean and more structure and avoid a lot of bugs. And you can also debug it by placing debug functions in the change state, like this object from the current state idle asked for a change to the next state, which is attack, move, heal, etc. So yeah, very powerful and useful things to do. And lastly, here we're going to set the new path goal, because this was the intended use for this signal, because we're going to reset the path goal to be 0 after we have generated a new path. So we're going to basically reset it. So this is what is calling my units to move. So if I go here to the RTS player, you can see here when the code move units to mouse, we have object called the new path, and under our units, the new path function now access and sets the object data new path goal to the coordinates we passed through the player interface here under the new path. And we access the state manager and ask it to execute a signal, which is basically to move the unit. We could also change this to say that we want to change the states to the move states, and this will also work as well. So as you can see, it's very clean and very useful to do. So that is basically the execution of the state code. So I'm going through the last project to do it step by step, and we're going to build everything here as you see. So let me just now jump ahead to the last project. So let's open here our new Godot, and let's open the last project part, which I have already duplicated and should be good to go to our project. So here we have our project last step, which doesn't have any of this code. So the first thing is I'm going to copy. So I just have copied the state scripts from the reference project back to this one, which was the last one. But of course, it's going to have a lot of bugs because its references have changed a lot. So let me go through the changes I have made in this project to make it a little more useful. So let me see here which script is more complicated to show you that we can fix a lot of the issues here. I believe action move or the selected or the main manager, which one is the most complicated one? So basically, whenever we are doing the aliases like these, I found a way to shorten the code even more and do it a lot more simple. So this here is actually duplicated code. This is technically correct, but as you can see here, the script data constant is duplicated in the code. So whenever you have this type of situation, you're going to simply grab the script you were preloading to grab the enums and replace through here. So this is going to work exactly the same, but now you can remove this line and keep just the aliases, which should also be useful enough. So as you can see, that is one of the changes that I did with a lot of the changes throughout the project. Another change I did was to replace these data constants to be renamed as object data. So this is a little more clear of what it does. And you can also replace through all the files. And as you can see, there's a lot of changes. So I'm going to replace all these files from data constants to be object data. So we're going to replace all of them, and this should also improve the readability of your code. So I also think you don't need this in the action move. And I have also deactivated this function here because we are not going to use. So previously we are moving the units by calling this function here from the action move to move the units, which basically allows the units to follow a path if it has a path. So this code now should be in the state of the movement itself, which we are also going to show you in just a second, but we are not using this function anymore. I also have renamed the object data called pathGo to be pathNewGo, because now the function from this variable is to execute whenever we have a new path, not the current pathGo. So let's replace this on the object constants and this one here. So let me first save before replacing, because this is going to change everything else. So as you can see, that is how it works. And also a big change I made was that previously we called these enums, constants, etc. Whereas now I'm calling them lists. So instead of data enums, now we should be calling them data list. So let me just replace these files. And as you can see, there's a lot of references. And we're going to replace all of them to be data lists instead of data enums. So that should be all the changes for the action move. Let's go to the action selectable. So here's a little more simple. We're going to just copy the preload code under our script data constants and remove this one. So the aliases is a lot more clean here. Now for data managers, we don't have aliases for those because they are also individual objects or interfaces, kind of love. So for data managers or any kind of manager we are preloading that basically exposes interface for us to manipulate that type of data information, we are going to keep those as individual preload objects and not use aliases because they are not being called for their enums or stuff. It's just the interface. So as you can see, to execute other functions. So I think those should be kept alone. So that should be all for the action selectable. Object data, so action names is going to be now called action lists. So here we are following the same principles as we did with the object data. So let's replace action names with action list. So object data, now it's called, instead of data enums, data list, and the object state is also using state list. So this is part of the new code. As you can see here we have these signals and these states, and this is under our, so if I try to show you here, is under our object state constants under the RTS scripts. So this just handles that. So these are all the changes for the constants. Now let's jump ahead to our object. Let's say here we want to change the main manager. I think I also did some changes. So the script act constants, it's a little poorly named. Now they are going to be called as aliases, which are going to be just action scripts, which I think works pretty nicely. So let's save before replacing. Now we should replace, and now it's a little more clear what it does. So I have not touched any other code, so this is basically it. Just save it. Let's now go towards our data main manager, and I don't think I have even changed this. I think I already did. Yeah, no changes here. And the main manager here should now work. So we are probably missing some things here. So object state, so yeah, the object data list now also has changed a little bit. So the constants under object data, I think I have a new entries here, which is the object states. So if I just paste the code here, you're going to see that I have added the object state here inside of the constants. So the state main manager can fulfill its requirements here. So this is all of the code for the state main manager. And the state idle code is this one, and everything has been fulfilled. So yeah, these are notifications, these highlights here, because we are not using those variables yet. So yeah, this is stuff in progress. But as you can see here, everything is working as it should. Now, for the basic unit, I have changed a lot. So yeah, this is a big mess. So let me see what I changed here. I think I changed these ones for these. And here we have another constant code. So this is script data constant, which should be this one. And yeah, this is just action scripts. So I also think I have added new ones. So we have now, yeah. So I have renamed act scripts to be act scripts. So yeah, a little more rename there. Let me save before replacing. There we go. Cow on physics stick no longer exists, so we're going to replace this function as well. What else I did? So for the aliases, so I have act constants. Oh yeah, I changed this because this is the action list. So I have renamed act constants to be now act names, because this is basically the action list itself. Now it's act names. Yeah, I have just inverted the order. Next we have object data aliases here, and we also have the states and the signals. So yeah, this is just like these. And so I basically, yeah. And I'm actually preloading the state manager twice, I think, here. But no problems, because the preload code is going to execute before the project. So this is not the same as doing a load. So I think we're fine doing it this way. You can preload both these ones because we are interested in the enums here. So yeah, I think this is fine. And I think it's also a little more clear. So this is one of the changes. So here under the physics process, on the unit, we also have changed this. So now instead of we accessing a given action like this, which was the action move to call it call and update physics, we're going to access the state manager and ask it to execute our current state. And the script state manager is not being declared. So let's add it here. And the object actions can go after the aliases. So it's a little more clear. What else we have here? So the startup, I think I also changed these variables here. So now I think I have 3 initializations. So yeah, the object states, and so we set the first state to be idle. then the move speed variable, and then we initialize all the actions. And now it's called different. I think it's act manager. So yeah, I have also changed act manager to be action manager. Yeah, that's a little more better name, I think. And it's only for this object. Interesting. So yeah, I'm going to try to keep this structure fixed for the entire thing, so it stays a little more consistent. So I think this is all of the actions, so all the changes. The new path function is also changed. So the new path function I have changed, which is not that one, it is this one here. So we first set the object data new path to the coordinates were passed through this function. So where we want to move basically gets to be stored here. And I actually passing a signal to move the object. I could in theory just change the state of this object to a movement, but I think having it as a signal to request to move is going to work a little bit better. So if we go towards our first state, so whenever we start this object, we're going to set its states to be idle, and we're going to execute it on the physics process. So if I go here to the idle state, which is this one, and I check here, on the execute state is not going to do anything, and once I enter this state, it's going to set its state of this object to idle. So whenever we ask for a new path and we pass and store the go towards this variable and we pass a signal, we're going to go here and execute that signal through the function call of execute signal through the script state manager, and is going to match the current state with the signal passed through this function. So if the state is idle and our signal is request to move, we're going to grab the new path goal variable we have stored previously to know where to move the units. And if that new path goal is not 0, so if we have a goal defined, we're going to say that we're going to access the script of action move, which is this one under the action list, and we're going to ask it to basically retrieve a new path. So whenever we pass the signal of request to move under the idle state, we're going to, if we have a path, generate a new path, then change the states to movements and set the path goal back to 0 because we already have a path. So we are basically now switching to the state of movement, and because we are doing this through the script state manager, is going to first grab the current state, exit out of that state, and enter the new state. And as you can see, this is the implementation. So the state movement now allows you to be executed, which in turn allows it to grab the current object path if it was generated and its size is higher than 1. If that's the case, then we are finally going to move towards the path. If our path does not have a size, we're going to go back to the idle state. And this time, instead of a signal, we're going to go it through the state manager and ask it to change the state. So fairly easy to do this and fairly simple, and I think this is a very much robust system. The last thing needs to be updated. I think it is the RTS player. I don't know exactly if it is or not, so let me see if that works. So this is the current state project, and no, they are actually working. And as you can see, this is not the reference project because it does not have the debug label. So as you can see, whenever the units are already in the move state, the signal of moving is not going to be identified, so they are not going to move to the new path. So this is done on purpose to just test the state machine. As you can see, if they are on idle and they have the signal to request to move, all of them move, but if they are already moving and I try to move them, they are not going to obey unless they finish the path and go back to idle state. So as you can see, our state machine is working. Now we have a very much robust system to make complex logic, and I'm going to advance this on further tutorials as we need. So we have actions, which are basically all the things an object can do. We have object data, which is everything they have. And now we have the states, which is basically what they are currently doing, and signals if we want to execute some type of behavior inside of those states at any given moment. So yeah, it's not a whole lot feature size. The project still has the same appearance, like nothing has ever changed. But with the goal of making object gather from trees, we have built a fairly complex system here. And now we should have the necessary tools to make a finite state machine. And it's also modular. It has state execution structures. It has signals so you can change whenever you want. And it also has a way to handle the transition fairly accurately. So I think this was a success. So we now have developed a way to make our units have states, which we're going to combine with a lot of attributes to to execute our actions, which are basically everything an object can do, which is get resources, attack, or move. Currently we only have implemented movement. So yeah, this is fairly complex, but as you can see, it basically allows you to do a whole lot of stuff just using this structure here. So I saw a comment that it was asking for these presentation files. So if you are a member of the channel, you can access these on the raw source project. So this file here, the swgb project.dry.io, is going to be inside of the project Google folder file. So you can grab if you are currently a YouTube member. So everything you saw on this presentation is going to be captured, and I think I'm going to also keep growing it as we need to explain more complex stuff, as we also need to build the prefab data, which is also very cool. So yeah, this is for future tutorials, and it seems I have made a mess here, but yeah, I am very happy with the result of the finite state machine, and I think you are also as well. So thank you guys for watching, and hopefully you found this tutorial useful. So thank you guys for watching, and I see you on the next one.